Hi guys, welcome to our lesson on structural concrete design part 2. So these are the topic we'll be looking at: concrete containing silica fumes. We look at high performance concrete. We look at lightweight concrete, concrete durability, then common causes of concrete cracking, then structure. Under that we look at structural cracking and non-structural cracking. So this is a continuation to our lesson on structural concrete design 1. So let's look at concrete containing silica fumes. Actually, what is silica fume? Silica fume is a byproduct that is obtained from the manufacturing of silicon and ferrosilicon alloy and it's gotten from high quality quartz and coal. It can also be called microsilica, or you call it condensed silica. Now, silica fumes have very fine particles, and the particles are usually between 0.03 micronewton meter and 0.3. Now, they are typically about 100 times finer than the particles of cement, and because of these extreme fine particles, they are able to penetrate spaces within cement particles that cement particles are not able to penetrate, and they are also able to fill the aggregate cement paste interface. This aggregate cement paste interface is actually the interface between cement paste and aggregate. So those spaces that are there, microfumes is able to penetrate them and fill them, and because of that, it will improve the packing of concrete and therefore increase concrete density. So it makes, because it has fine particles, it makes it very, very reactive. Micro or silica fumes is very reactive, and because of that, you can only replace about small portion of Portland cement with it, usually between 3 to 5, a maximum of 3 to 5% of cementitious materials is replaced with silica fumes for normal concrete. Now, such percentage, however, does not produce high performance concrete. This percentage will just give you something of normal concrete. But the silica fumes is also expensive, or it's very expensive, so usually it's not used for for economic reason. It is usually used to achieve a certain aim. So since concrete containing silica fumes are usually very well packed and they have a reduced volume of voids, they are usually very durable. So concrete containing silica fumes are usually durable, and the largest use of silica fumes is in the production of concrete with enhanced property. Those concrete are known as high performance concrete. And so the presence of silica fumes in concrete, it reduces bleeding because the concrete will be homogeneous. So it reduces bleeding and it results in possessing high resistance to abrasion. So concrete containing silica fumes, if properly mixed, will not have a weak top. So it will not be so vulnerable to abrasion. So concrete with silica fumes higher strength. Its presence of concrete also enhance the effectiveness of super plasticizer. So silica fumes are usually used with super plasticizer, and and because of this combination, they will reduce the water requirement. So with a little water, you can achieve the required workability. And so also its presence also enhance curing. So generally for concrete of equal strength, the reduction in permeability due to a long period of curing is greater in concrete containing silica fumes than in Portland cement concrete only. So let's look at high performance concrete. Now, high performance concrete are simply concrete with enhanced properties. That is concrete that a particular required properties have been enhanced, and they do not necessarily contain materials that are not there in normal concrete. They contain the same material that are in normal concrete, just that they are different is that these materials are logically proportions. in a way that it will give the required enhanced properties. Now, the meaning of high strength, for instance, now, high performance concrete also usually have high strength. And in terms of strength, there was a time that 40 megapascal was considered high strength. Later on, 60 megapascal was considered high strength. But with the improvement and innovations in the concrete industry, what in for this lesson, what is considered as high strength is actually concrete in excess of 80 megapascal. And as such a strength, the difference between cube strength and cylindrical strength is negligible. So at such different, you don't even need to say whether it's FCK or FCU, it doesn't, they are the same because at that high strength. Now also note that high performance concrete was formerly known as high strength concrete, and this is because strength was usually the required enhanced property. But however, in many cases, there are other properties that are required. It could be high durability or high modulus of elasticity. So it's not only strength that is required enhanced property. And that's why it's now called high performance concrete and not just high strength. Okay, so still on high performance concrete, these are the constituents of high performance concrete. They usually include a good quality aggregate, not just any aggregate. Then ordinary Portland cement, but at a very high content, usually between 450 to 550 kilogram per meter cube of concrete. Sometimes rapid hardening cement may be used when early strength is required. That is depending on what you want. Now, there's usually silica fumes, usually between 5 to 15% by total mass of the binder or by total mass of cementitious materials. Other mineral additive, other cement blend can also be added like fly ash, GGBS may also be added. Now, super plasticizer at a high content, usually between 5 to 15 liters per meter cube. Super plasticizer is very, very important. And of course, water, with water at a very low content. So because of the presence of super plasticizer and silica fumes, you can use water at a very low content and still achieve the required workability. And so high performance concrete can therefore be said to be a logical development of concrete containing silica fumes and a super plasticizer. It is also important to be sure that the super plasticizer is compatible with the selected Portland cement. Don't just use any super plasticizer. Make sure they are compatible with the selected Portland cement. Now, let's take note of this, that what actually makes concrete high performance, it is the very low water binder ratio. That low water, because water cement ratio affect the strength of concrete. The lower the water cement ratio, the higher the strength of concrete you will achieve. And so water is always in concrete for you to you only need water to achieve the required workability. It's not as if the water is needed much. The water needed for hydration is very little. But the other ones we put is just to achieve the required workability. So if there is a way that you can achieve a required workability with the very low water cement ratio, you will have a high performance concrete. And so the use of super plasticizer and silica fume allow the use of very low water binder ratio. The ratio is usually below 0.35 and often around 0.25 and 0.2. And so another major contributor to the high performance of this concrete is the presence of silica fumes. And silica fumes, because of its extreme fineness, it is able to fill the spaces between cement particles and the aggregate cement paste interface. And because of this, it results in a highly dense concrete. And once the density is increased, it means the volume of voids is reduced to minimum. And this is what makes the concrete a high performance. Now, what's the mixed proportion for high performance concrete? There is no standard mixed proportion, there is no typical mixed proportion. However, the following successful mix have been used to achieve a high performance concrete. So you can see mix A here. It's a mix. You can see mix B, you can see mix C, mix D. These are mix that have been used in previous times to achieve a high performance concrete. They are not typical mix. You can design your mix and achieve what you want. So like this mix A, it gave a strength of 93 megapascal. This one 83, this one 114, this is 111 megapascal. Now let's talk about durability of high performance concrete. The very fact that high performance concrete is particularly dense, I mean it has a dense structure of for iron hydrated cement paste. So it has a discontinuous system of capillary pores. That means a pore volume has been reduced. So that will give resistance of such concrete to penetration of external attack or external fluid that will cause a durability problem. And so this is particularly true with respect to ingress of chloride into concrete, and it makes high performance concrete far more durable than normal concrete. So now let's look at lightweight concrete. What are lightweight concrete? In normal practice, the volume of in normal practice, depending on the volume of aggregate density of concrete is usually between 2,200 to 2,600 kilogram per meter cube. That results in about 22 to 26 kilonewton per meter cube. Remember that in our design, Euro code recommend using 25 kilonewton per a meter cube. However, occasionally the use of concrete with lower density is required. You need concrete with a very low density. Usually when you're doing construction on the ground with very low bearing capacity, you don't want to load the soil with much load. So on such occasions, you might require a lower lightweight concrete. Now, typically this lightweight concrete, this concrete are termed lightweight concrete, and they are usually between 3 to 18.5 kilonewton per meter squared of density. Now, lightweight concrete are known to exert less pressure on formwork, and as such require cheaper formwork than normal formwork. So because the density of concrete is less, you might not need much formwork than you will need in normal concrete. So they typically have higher thermal insulation properties than normal concrete. But on the other hand, we need to also remember that lightweight concrete require higher cement content than normal concrete. So because of that, they could be little more expensive than normal concrete. So even you're making comparison in terms of cost, you need to compare the advantage of using less formwork and also the disadvantage of using more cement. So you need to make a real comparison to know if it's advisable to use a lightweight concrete or not. Now let's look at classification of lightweight concrete. Now the density of concrete can be reduced by replacing some of the solid materials in the mix by void. There are three possible locations in concrete where the A voids can be located. It can be, and this is formed the basis of classification of a lightweight concrete. So one, it can be within the aggregate. We call that one lightweight aggregate concrete. It can be within the cement paste. We call such cellular concrete. And it could be between the quartz aggregate particles, and we call that the no fines concrete. So let's quickly look at lightweight aggregate concrete. Lightweight aggregate concrete are produced using lightweight aggregate. In this case, it is the aggregate that is lightweight, usually the quartz aggregate. And the main characteristics of lightweight aggregate is high porosity, which results in low specific gravity. That means the aggregate himself is porous, it has lots of voids. and so it becomes lightweight aggregate. So some lightweight aggregates can be like volcanic cinders, the scoria. They occur naturally, while some others, like expanded clay shell, are manufactured from natural materials or industrial byproducts. So you can see example of a lightweight aggregate here is scoria, which is a natural lightweight aggregate, those case. Now, still on lightweight aggregate concrete. Lightweight aggregate concrete usually have lesser strength than normal concrete for the same cement content. However, it has been produced up to a strength of 790 megapascal. So usually lightweight aggregate concrete is between 0.3 to 70 megapascal. Now, because the pore system in the lightweight aggregate concrete is discontinuous, the porosity of the aggregate does not influence the permeability of the produced concrete, so which is controlled by the permeability of the hardened cement paste. So because of such reason, there might not be serious durability problem in lightweight aggregate concrete. Now look at some manufactured lightweight aggregate concrete. We look at scoria the other time. This is shell. Okay, scoria is a natural lightweight aggregate. This is a manufactured lightweight aggregate. This is shell, and this is expanded clay. And you can see a sample of a concrete produced with expanded clay. You can see it's even decorative in nature. So still on lightweight aggregate concrete, still on lightweight concrete, the next one type is what? A cellular concrete. And these are lightweight concrete formed by the introduction of stable A voids within the hardened cement base. So in this case, the void is within the hardened cement base. The voids can be produced by gas or by air. Hence, this concrete can also be called gas concrete or aerated concrete. They usually don't contain coarse aggregate, so it's just fine aggregate with a hardened cement base that has lots of void. So usually aluminum powder is introduced into the mix and it reacts with hydroxide of calcium or alkali from the cement to liberate hydrogen bubbles, which then expand the cement base. Cellular concrete have low strength, typically not more than 10 megapascal in compressive strength. So you can see example of a cellular concrete. They have lot of voids, just fine aggregate and lots of voids in the hardened cement base. The last one is a no fines concrete as the last type of lightweight concrete. And these are forms of lightweight concrete obtained when fine aggregate is omitted. That means it's just the cement, hardened cement base and coarse aggregate. So when conventional aggregate is used, density ranges from 16 to some 1600 to 2000 kilogram per meter cube. But by using lightweight aggregate, it may further be reduced to 350 kilogram per meter cube. Now, though strength is lower than normal strength, maximum about 15 megapascal, it is still sufficient for the use in structural members or load-bearing wall. Now, because of their low bond strength, reinforcement is usually not used. It's usually not used. And also, I feel because of the porosity, I know fines. So if we use reinforcement, we'll have problem of rusting because of the permeability of the resulting concrete. So now let's look at concrete durability. What is concrete durability? Concrete durability is usually the ability of concrete to resist deterioration, the deterioration process that may occur as a result of interaction with the environment or between its constituent material or their reaction with contaminants. So concrete is said to be durable if it continues to perform its intended function of maintaining required strength and serviceability during the specified or traditional service life. Now, inadequate concrete durability occur as a result of deterioration. So once deterioration occur, that is, we start having a durability problem. Now, this deterioration can be caused either by external action or by internal action within the concrete mass. Several processes of concrete deterioration involve increase of aggressive fluid. So it's usually the penetration of aggressive fluid from the surrounding into the concrete. So similar deterioration can cause by internal action, which usually involve movement of fluid, of moisture, or movement of moisture that can cause one problem or the other. There are three principal fluids that can penetrate concrete mass, and these are relevant in its durability. These are water, either it is pure or it is carrying aggressive ion. Another one is carbon dioxide, and the third one is oxygen. So the movement of this fluid into concrete causes a durability challenge. Now, the ease with which this fluid penetrate and move around a concrete mass depends on the concrete pore system. It depends on the concrete pore system, and this is what determines the durability of concrete. The ease of movement is usually referred This ease of movement is usually referred to as permeability. So once the permeability of concrete is high, we start having durability concrete of issue. And so the aim of an engineer is to design a concrete with as minimal permeability. The ability of concrete structure is determined by the nature of the pore system within its hardened cement paste and that of the region around its aggregate cement paste interface. This aggregate cement paste interface is also where early thermal cracking concentrate. Thus, it plays a great role in the concrete permeability and hence durability. Aggregate cement paste is the region between hardened cement paste and aggregate where that cement paste, hardened cement paste bond aggregate together, that interface, there's always some micro pores in that interface. And the level of the micro pores determine the permeability of concrete and in turn determines its resistance to deterioration. Now, pores in aggregate usually do not contribute to permeability issue because they are often discontinuous. So now let's look at common durability issues in concrete. The first one is chloride attack. Chloride attack occurs as a result of dissolved chloride that are sometimes penetrate concrete members through the concrete pores or crack. This usually take place through absorption or diffusion. So when you have this dissolved chloride, they are dissolved in water and they have a way of penetrating into concrete mass. So the common source of chloride includes seawater, the icing salt. Now, chlorides can also be from within concrete mass. This happens when they have been incorporated into the concrete mix through the use of contaminated water or seawater, or whether it find in the aggregate or the admixture. But however it finds its way into concrete, it will bring problem to the resulting concrete. Now, the presence of this chloride is not generally a cause for much concern in plain concrete, but it accelerates steel reinforcement corrosion in reinforced concrete. And this is one of the major causes of deterioration and degradation of reinforced concrete structure in marine environment. So if not for reinforcement, chloride wouldn't be a big issue because it doesn't really attack concrete. But because of reinforcement, when it gets to reinforcement, reinforcement will rust. And when the reinforcement rusts, it will expand and cause more cracking on the concrete mass itself. So what is the solution to chloride attack? The solution is to provide adequate and quality cover to reinforce. Take note, the adequate. That is why some design state the minimum requirement for cover. It's a concrete cover must be not less than the diameter of the reinforcement. So that means the cover must be adequate. And then the quality means that the permeability of the concrete used as cover must be as low as possible so that it will be able to resist that concrete will be able to resist the penetration of chloride. Now, permeability of concrete used as cover should be at minimum. I've mentioned that before. So let's look at another durability challenge, sulfate attack. We have sulfates of sodium, sulfate of magnesium, and potassium and calcium. They exist widely in soil, they exist in groundwater, and they exist in seawater. Now, these salts in their solid state do not affect concrete. However, when in solution, they attack hydrated cement paste. The attack is usually by decomposition of hydration products. This one is unlike chloride. Chloride attack the reinforcement, it does not attack concrete itself. But this one attack concrete itself because it attack the product of hydration, usually the calcium silicate hydrate and calcium hydroxide. So when it dissolve this, it will dissolve this product of hydration to form new compounds, and mostly those new compounds are soluble. So because they are soluble, they will be leached out. They will be leached out. So that means as they are leaching out, the concrete is losing mass. The concrete is losing mass because of the reaction between the sulfate and some product of hydration. Now, as it's losing mass, it's not as if the concrete is losing mass from the aggregate, it's actually from the hardened cement paste, which is actually a binder. So as it's losing mass, it means that it's losing binding strength. So concrete subjected to such attack may result in cracking, in spalling, in loss of mass, or in weakening of binding strength of hydrated cement in concrete. What are the prevention? Provision of adequate and quality cover to reinforcement, and sometimes use of solvent-resisting cement. Permeability of concrete used as cover should be at minimum. The next one we are looking at, next durability challenge, is the acid attack. So concrete are alkaline in nature, as such they possess less resistance to strong acid and compound which may eventually convert to acid. As with other chemical attack on concrete, acids attack concrete by decomposition of the product of hydration of cement and subsequent formation of new compound, just like we discussed in sulfate attack. So the most vulnerable cement hydrates of acid attack is what? The calcium hydroxide. Although calcium silicate hydrate can sometimes also be attacked. Acid react with calcium hydroxide to form their respective calcium salts, which is usually leached out of the concrete mass depending on their solubility. So just like a sulfate attack, acid will now attack the product of hydration and then change them to other compounds, and these other compounds are soluble, and because they are soluble they will be leached out. Now acid attack may be from soil or groundwater resulting from decayed plant or dissolved carbon dioxide, industrial or agricultural effluent. It could also come from water and wastewater treatment facility, offshore oil storage tanks, and from acid rain, which consists mainly of sulfuric acid and nitric acid. It was also note You should also note that for acid attack and sulfate attack, if the concrete is not in water, the water does not come, there might not be big problem after decomposition. But if the concrete is in water, like most you're constructing your sea structures in the sea, bridge and all those things. So once the attack occur, the soluble component compound will be leached out by the water, and that is what will actually cause a loss of mass, which is a big problem when we are talking about acid and sulfate attack on concrete.